Hi guys. We'll just give it a sec for other people to show up. Anybody have any quick questions on the homework they want to ask before other people show up for the class? I have the chat window open too if you wanted to put it in there. No homework takers? Excuse me. Excuse me. How you guys doing?
Good, thank you. And bless you.
Okay, we'll just give it another sec. So we can talk about homework at the end of class, but we have a few minutes while we're waiting for other people to show up. If anybody wants to ask a question on the homework, I posted a whole bunch of homework problems yesterday. Oh, I just had them up on our class page, right? I actually made a whole section for it, like the homework solutions, just so you can see. But these are like the individual questions that I put up yesterday. Anybody has any questions on those or on other things? Some of them were long, which is why they got put up online instead of discussed in class. No? Okay. Alrighty. Well, today it's very exciting. Today we're going to start chapter 2.5, which is about the natural log. So we're going to spend the first part of the class talking about the properties of the log, and then, what are we going to think about it? How are we going to, take the derivative, things like that. And then we're going to go into a technique called logarithmic differentiation. It's a really important technique. It's actually going to help you quite a bit because it helps reduce, excuse me, my allergies are going crazy. It helps reduce the complexity on a problem. When you need to take the derivative of something that's got a lot of stuff going on, taking the log of things will help you actually reduce it so that you can take the derivative more simply. But we're going to get to that, in the second half of class. Okay, so let's go ahead and get started. Oh, by the way, don't forget, today, Thursday, we have a bunch of things due, right? Our homework for chapter 2.1, 2.2, 2.3 is due at midnight tonight. And then we also have a quiz that opens up today at noon, and it's open until noon tomorrow. Don't forget, you need to start the quiz no later than 11 o'clock tomorrow morning so that you have time to complete the quiz, take a picture, and upload it to Canvas without any difficulties. Okay, so let's go ahead and get started. So chapter 2.5. So we're talking about the natural log, ln, which I've been writing as ln in cursive so that it doesn't look like a 1 times n. ln, so there's a whole bunch of different logs of different bases, but we're talking about log base e. Okay, basically, e is our transcendental number that we talked about yesterday in class. But it's so common, we use it so much that we get it natural log. We give it its own log symbol. Okay, so basically, our natural log has a domain that's basically only positive numbers, right? We'll draw a picture of the graph in just a minute. But our domain, our input values, can only be greater than 0. Okay, this whole function asymptotes at x equals 0, right? And like it's just not even defined for values that are less than 0 or less. Our range, our output values, you can have any possible number for output, right? I mean, all possible values of y are possible. Okay, so we also want to talk about the natural log is the inverse function for e to the x. Inverse function for e to the x. Okay, so just kind of think about like natural log, ln of x, and e to the x are two sides of the same coin. Okay, one's an inverse of the other. All right, so let's talk about properties of our natural log. Okay, so properties of our natural log. So we just said this one, our domain, basically is basically 0 to infinity, right? So these brackets here, these mean not inclusive, right? And then our range, minus infinity to positive infinity, all possible numbers in our range. Okay, and we can see that when we do our graph. So if we do our graph, right, so our natural log function goes like this. Okay, so as we get closer to 0, our function, basically just drops right down, heading off to minus infinity here. There's an asymptote here at x equals, I'll draw that in, there's an asymptote here at x equals 0, and the function is just not defined for values less than or equal to 0. So for all x values and for all y greater than 0, if I have natural log e to the x, going to equal to x, and e to the natural log of x, I'm sorry, e to the natural log of y equals y. Okay, these are like properties of our inverse, right? This is kind of like, this is a common property in logs, right? So if I take if I take a log of the same base, like so if this was log base 2 of 2 to the x, this would also be true. Like 2 to the natural log base 2 of y, this would also be true. So this is sort of a generic property of logarithms, okay? And when we're dealing with our inverse, right, because e and ln are inverses of each other, right? They have the same base, essentially, then this is true. Okay. Ln of 1 is equal to 0. Ln of e is equal to 1. Okay, we've talked about this before when we were doing our derivatives, right? This is included in our derivative of e to the x, right? We did our chain rule. We said there's a natural log of e, a natural log of the base in there, but we don't see it because the natural log of e is equal to 1. And this is true because they're the same base. Okay. Right, so this is what happens, right? So as x goes to positive infinity, this is an x, as x goes to positive infinity out towards this way here, right, my natural log function is heading off. It's forever increasing. It's always increasing. Okay, and I go in the opposite direction. The limit as x goes to 0 from the right-hand side. I can't say the limit as x goes to 0 without specifying that I'm going to just the right-hand side, because the function is undefined on the left-hand side. So I have to specify this is just a right-handed limit because the function's not defined on the left. Okay, now, so as I head towards 0 from the right-hand side, my function itself is heading towards minus infinity. Okay, here's what we're looking at. Now, let's see, I'm going to do this in a different color so you can see. I said that these were inverses of each other. Remember the whole property of our inverse, there's a symmetry across the line y equals x. I'll draw that line y equals x right here. And I'll draw my oops, I'm not drawing that very well. There's this, goes right through that spot there. I'm not the best artist here. Okay, this is e to the x. Should be a smooth line right through. This is y equals 1. And then this is going to asymptote on this line here. So this green dashed asymptote corresponds to my e to the x function. We did this yesterday, right? So you can see there's going to be a symmetry here across the line y equals x. That's part of our definition for inverses too. Just if you ever forget like how these two graphs look, you just remember how one of them looks and then draw the symmetry across the line y equals x. Okay. All right, let's talk about derivatives. So for all positive x values now, if I take the derivative of my natural log function, my derivative is 1 over x. Okay, so my first derivative is positive, right? This is a positive value, which means that my function is increasing. You can see it here in our graph, right? This function's forever increasing, right? And then if I take the second derivative, okay, if I take the derivative of 1 over x, if I take the second derivative, of ln of x. Remember we did this in chapter 1, but we did it the long way, right, with the definition of derivative. Now we can do the power rule when we go to take the second derivative here. Okay, but this one here is going to be negative 1 over x squared. So second derivative is negative, right? What does it mean if our second derivative is negative? It means we're dealing with concave down. That's what we're looking at when we look at our natural log function, right? We're looking at an always increasing function that's always concave down. So let's just write that down. So our natural log function is strictly increasing on our domain, right, which is all x values greater than 0. And the graph is always concave down. Okay, not too bad. All right, let's go into some examples here. So I've got my lecture examples for chapter 2.5. This should be up on our Canvas page 2. So I'm looking at example number 1. I want to be able to calculate the derivative of minus x plus x ln of x. This right here, I'm going to have to do the product rule on, right? So let's think about that one. This I can just take with the generic power rule, okay, but this one I have to do the product rule. So let's go ahead in pieces. So minus x, that derivative is minus 1. Plus, there's a product rule. I'll write that down in here. Product rule. Plus, I have to do my derivative. So I'm going to say the first times the derivative of the second, 1 over x, plus the second ln of x times the derivative of the first. Okay, now I can clean things up. It says minus 1 plus x times 1 over x is 1 plus ln of x. So minus 1 plus 1 is equal to 0. Ln of x, this is just ln of x right here. We're going to see this next semester when we do antiderivatives, when we do integration, right? If I go to integrate the natural log of x, this is what I get. This is my antiderivative of the natural log of x. Okay, so we're kind of throwing out these pieces for you, okay? So it won't be completely unfamiliar when you see it again next semester. Example 2, we're going to calculate the derivative of natural log of, this came out really small in type, natural log of e to the r plus r all over 5 plus the natural log of r. Okay, so this one here, we have our quotient rule. Okay, the first thing I want to mention is, though, remember your properties of logs, ln of e to the r plus r. I cannot distribute the natural log to both of these terms. Absolutely cannot. This is equal to the natural log of e to the r plus r. That's it. I can't distribute. Okay, so don't think I'm going to distribute the natural log and I'm going to take, no. You just have to work it. It's just a group. Okay, there are properties of logs that allow us to break things apart and combine them. But if it's addition like this within our argument, that's it. It's as close as it's going to get. So quotient rule is where we're at. Okay, so let's do that. So quotient rule says bottom 5 plus ln of r times the derivative of the top. Remember, you can do u substitution on here if you want. So if I say, I'll go u equals e to the r plus r, du equals, I have to take the derivative of this, right? This is going to become with respect to r. So I'm taking the function with respect to r. So it's going to be e to the r plus 1. Okay, so that's what I need to think about. So now when I take the natural log of u and I take that derivative, I'm going to go 1 over u times du is how I need to think about it right here. Okay, so the derivative of this one, okay, is going to be 1 over u, 1 over e to the r plus r, times du, which is e to the r plus 1. Okay, so this is e to the r plus r, this is e to the r plus 1. Okay, okay, minus, okay, the top, ln e to the r plus r times the derivative of the bottom. The derivative of 5 is 0. Derivative of ln of r is 1 over r. And that's all over the bottom quantity squared. And I'm basically done. I should have probably drawn it out on whole one line, but I used this spot right here. It's like scrap paper. I'll put a bracket around this so you can see that's all in the numerator. Okay, that's it. You want to put things together, make it look nice, bring the 1 over r out front, fine. Okay, but otherwise, you're basically done right there. Okay. Example 3, calculate the derivative of the natural log of minus x. Okay, when I go to take this derivative, natural log of minus x, that's going to look like, so my u is equal to minus x. My du is equal to minus 1. So this is the natural log of u. When I go to take that derivative, I'm going to get 1 over u times du. Right there. Okay, so now we want to think about that. 1 over u, 1 over minus x, times du times minus 1. This is equal to 1 over x. This is kind of like our exploitation of, you know, how I can think about breaking things apart within my natural log. Okay, I've got a constant term times my x value, and I can bring things out like that. Otherwise, just leave it. This is fine. Okay. So let's talk about some algebraic properties for our natural log. So our algebraic properties of our natural log are going to look like this. If x is greater than 0, the natural log of 1 over x is equal to minus the natural log of x. This comes from our properties of logs. So let's write that down. Properties of logs. Okay, so this is like, I've got a thing that I'm dividing. Okay, so this is like saying I'm going to go natural log of 1 over x is equal to natural log of the numerator minus the natural log of the denominator. Okay, the natural log of 1, that's equal to 0. So then we have minus ln of x. That's where this comes from. It's not magic, but it's just basically properties of logs. Well, x greater than 0 and a greater than 0. A is a constant term. Ln of ax equals ln of a plus ln of x. This is also, again, a property of log. This is true for any log, a log of any base. Okay, these are like generic properties of logs. Again, x greater than 0, a greater than 0. This is, again, if I say ln of a over x, this is like our property of log that we just did in question part 1 here. This is going to look like ln of a minus ln of x. Properties of logs. We're going to exploit these when we do logarithmic differentiation in just a minute. Okay, for all x greater than 0 and all rational numbers r, looking at ln of x to the r. Okay, this is a property of log 2. Exponent.
Professor,
Yes.
can you put it up a little bit? Thank you.
That way, is that good?
Past number 1 is fine. I just need to see that.
Okay, no problem. So this is another property of log. This is our exponent rule, right? I've got ln of x to the r. I'm going to bring the r out front. Ln of x. This is true for any base of log. Okay. We're going to use these properties when we go to do logarithmic differentiation, and it's going to make it our life a lot easier. Give you guys a minute to finish writing that, and then we'll talk about logarithmic differentiation. How's it going? You guys all set? What chapters are on the quiz this week? The quiz this week is chapter 2.1, 2.2, and 2.3. So the homework that you're passing in is what the quiz is going to be on. You guys all set with this? I'm gonna move the page to talk about logarithmic differentiation. I'll leave it like that. How's that? Okay. So I'm going to write down the steps, the process of doing logarithmic differentiation, and then we're going to do a couple examples so that you can see how it actually works. But I'll write down the steps so that you have it in terms of like steps to follow. These are just guidelines. These are things that like I kind of came up with as I was working through logarithmic differentiation. Okay, so the first step is we're given a function y equals some complex function, right? So the first thing I want to do is I want to take the natural log of both sides of the equation. Oops. Take the natural log of y equals the natural log of whatever y is equal to, right? Whatever I do to one side, I have to do to the other, balance things out. My next step is I'm going to use my properties of logs, these things that we just talked about, the multiplication property, the division property, and the exponent property, right? These things that we just did here. I'm going to use that to break this big equation up into smaller chunks, like individual chunks. Now, some of those pieces are going to be the natural log of x squared, the natural log of something, something, something. Some things we can clean up. Some things are going to be the natural log of something, okay? But it's going to be at least in small bits instead of one big conglomerate thing, okay? Our third step that we do is we're going to take the derivative now of both sides, and that's important. We tend to think f of x equals something, and we go f prime equals what? We think of that as like, I'm being told what to do. I have to take the derivative of this thing. But really what we've done is we've taken the derivative of both sides. F of x equals something. F prime is the derivative of f of x, right? And then we're actually following through on what the rest of the derivative is. That's going to be true if we have the natural log of f of x, natural log of y. We have to take the derivative still of both sides. And remember your chain rule. And this comes into play because if I've got natural log of y equals the natural log of some function, what I'm going to get is I'm going to say the natural log of y, taking that derivative, it's going to look like this. 1 over y times dy dx. And that's going to equal to the rest of the function. Right, we're taking that natural log, we're going to take that derivative, but this is what I have on my left-hand side of my equation, 1 over y times dy dx. This is, you know, our chain rule. But basically what's going to happen is we're going to solve for this dy dx. So I'll put a little circle around this here because we're going to solve for that. So keep that in mind. That's important. Okay, so step 4. Step 4 is going to be, we're going to combine all the like terms on, we have our, on this side, 1 over y dy dx on one side of the equation. On the other side, we've got all this stuff going on, all the derivative stuff, right? So you have all these derivative things happening, right? And we're going to combine all the like terms. Okay. It'll make more sense when we actually go through an example, but I want you to have the steps ahead of time. All right. Step 5, we're going to solve for dy dx. I'm going to circle this in orange to remind us that it's the same dy dx that we just circled over there. How we solve for dy dx means I'm going to multiply both sides by y, right? Which means I'm going to multiply both sides of the equation by y. So on one side I have dy dx equals y times all this stuff, right? Step 6, I don't want to have y times all this stuff. I want to actually substitute back in for y. So y was equal to my original equation. Y equals the original, right? So I'm going to substitute back in y equals, and I'll write down original equation. So what I'm going to get is dy dx equals my original equation times the derivative. Okay. And then step 7, I'm just going to write it and make it look pretty. Dy dx equals whatever our original equation is times our derivative. Okay. And this is important because you want things in terms of x, or whatever variable you're working with, and not y times that function of x. Okay, so this is like a step. This is making it look pretty. Okay, but I don't have to combine anything. I can just leave it as this times that. It's going to be this kind of equation times that kind of equation. Don't worry about combining it. Okay, this is an alternative to doing things like the quotient and the product rule. It is a shortcut method. Even though it seems convoluted, I've got 7 steps I have to follow. Why can't I just do the quotient rule? You absolutely can, except we're going to ask you to do logarithmic differentiation on a midterm and a final exam. It's a tool that you'll need to know how to do. Okay, so make sure, right, that you're adept at doing this. Okay, where you're adept at following these steps here. And we're going to go through 2 examples today, and then we can talk about homework problems for this extensively on Monday. Monday, sorry, we don't have school on Monday. On Wednesday. Okay. Yes, I'll have this. I'll give you a minute to finish writing all that down, and then we'll go through a couple examples. You guys good with this? Anybody need more time to finish writing? If I don't hear anything, I'm gonna start the example. Okay. All right. So we've got this y equals, I don't know why my my text font is coming out so small here, but y equals x squared plus 1 raised to the 6th power times e raised to the 5x cubed minus 2x power all over radical x to the 4th plus 7. Okay, so I want to find y prime. Wow, that's going to be a pain, right? If I do the quotient rule, I'm going to go bottom times the derivative of the top. Oh, that's going to be a nightmare. I have to do the product rule too. Okay, product rule in addition to my quotient rule. Okay. So I'm going to think logarithmic differentiation. When I see stuff like this, right, I think logarithmic differentiation because it's going to break things apart. Okay, so if I take the derivative as it is, it's going to be messy. So let's do logarithmic. Logarithmic differentiation. Now remember, we are going to ask you specifically on a midterm and on the final, we will say use logarithmic differentiation to solve for y prime. Okay, so you will need to know how to do this, okay? But you are also free to use this method instead of the quotient rule or whatever, okay? Unless we tell you specifically use the quotient rule to find the derivative, you can use whatever method you want. Okay, so the first thing I need to do is I'm going to take the log of both sides, okay? So I'm going to go the natural log of y equals the natural log of, and I'm just going to repeat this for myself here. So x squared plus 1 raised to the 6th power times e to the 5x cubed minus 2x all over radical x to the 4th plus 7. Okay, my first step, taking the log of both sides. Okay, which means now I can start using properties of logs. So I'm going to write that down, a little note to myself. Use properties of logs to break apart. Okay, so my, just on the outside when I'm looking at it, I've got here's a term being multiplied by another term being divided by this whole thing. So the first thing I have is the numerator and the denominator, which means I can split them apart as a subtraction. So I'll do that part first. I'm just going to say ln of y equals. So I've got my numerator ln of x squared plus 1 raised to the 6th power times e to the 5x cubed minus 2x minus the natural log of, I'm going to write x to the 4th plus 7. I'm going to call this raised to the 1/2 power because I'm going to exploit my exponent rule later. Okay, because this is radicals that makes it an exponent with the 1/2. All right, now look, I've got a product. I've got a term being multiplied by a term, so that means I can separate those with addition. So I'm going to do that. So I'm going to go the natural log of x squared plus 1 to the 6th plus natural log of e to the 5x cubed minus 2x minus ln x to the 4th plus 7 to the 1/2. Okay. You guys ready? It's a lot of steps in this, but it's actually a little bit more straightforward than doing quotient rule. Okay, so let's exploit our exponents. Right, we're going to bring these down. So this is going to become 6 times the natural log, x squared plus 1. Now, look, I've got the natural log. First, what I'm going to do is I'm going to put this in parentheses to keep myself honest because it's an exponent, but also natural log of e. If we write it down like this, it's going to look like 5x cubed minus 2x times the natural log of e. I'll write it like that so it's clear. Minus my exponent, 1/2 ln x to the 4th plus 7. Don't be lulled into a sense that you can distribute your ln here. Remember what we said. If it's ln of something, of a block, it stays as a block. Okay, I've got x squared plus 1. I've got things that are being added and subtracted. They stay together inside the ln. Okay, it's only when I've got a product of multiple terms that I can break those up into the addition of the natural logs. But if it's adding, I'm done. All right. Now here, this ln of e is equal to 1, so I'll do one last step. 6 ln x squared plus 1 plus 5x cubed minus 2x minus 1/2 ln x to the 4th plus 7. And this is equal to the ln of y. All right, so all we've done so far is just take the ln, natural log, of both sides of the equation, and we've exploited our properties of logs to break this up. So already, instead of this big conglomerate of a function, I've got 1, 2, 3, 4 different pieces that I now can work on individually. Okay, so now I'm going to take the derivative of both sides. Don't forget to take it of both sides, otherwise the equation won't be true. Okay, so if I take the derivative of both sides, remember we said about our chain rule. So the derivative of this is going to become actually, right, derivative of this is going to become 1 over y times dy dx equals. Okay. Now, my linearity property of derivative says I can take the derivative of each piece. Watch out, I have to do the chain rule on all of this. Okay, and then this 6 is just a constant term that just gets multiplied through. Okay, so this becomes 6 times, remember this is our u, so this becomes 1 over squared plus 1 times our chain rule, 2x. Okay. Plus, these are just polynomials, right? So the derivative of 5x cubed is going to become 15x squared minus 2x, right? Minus 2. Minus the 1/2 is a coefficient. This right here, remember, I go 1 over my argument plus 7 times my chain rule, right? So this is 4x cubed. Alrighty, doesn't that look easier than my original chunk of stuff? Okay, so let's kind of put things together, make it look a little nice, and then we'll worry about this one right here. So 1 over y dx equals, so 6 times 2x, this becomes 12x, x squared plus 1, right? This is plus 15x squared minus 2 minus, so 1/2 times 4, so that becomes 2x cubed, x to the 4th plus 7. Okay. All right, good. So now remember this bit right here. Okay, I have to multiply both sides by y, like this. Whoops. Multiply both sides by y to solve for dy dx. So I'll write that down here. I'm going to solve dy dx, because dy dx is my derivative, right? So I have to solve for that, get that alone. So I'm going to go dy dx equals, I'm going to go like this, y times 12x all over x squared plus 1 plus 15x squared minus 2 minus 2x cubed all over x to the 4th plus 7. Okay, I'll just move the y out front. Okay. Now I need to substitute back in for my y. You make sure you do that process so that our derivative is all in terms of x. I don't have a y in there hanging around. dy dx equals, my y was equal to, y is equal to this. My y is equal to that, whoops, sorry, again. My y is equal to this function right here. Right, this is my y. So I'm going to substitute this blob in for my y. So my y goes x squared plus 1 raised to the 6th power times e to the 5x cubed minus 2x all over x to the 4th plus 7 radical. And I'll put a bracket around it. Times my derivative that I just figured out, 12x x squared plus 1 plus 15x squared minus 2 minus 2x cubed x to the 4th plus 7. And then we're done. And put a big circle around it. Okay, it's actually more straightforward than trying to do the quotient rule on this thing. Okay, you can, but we're going to ask you to do logarithmic differentiation, so you want to be able to know how to do it. And it's a good tool to know how to do. The methodology that's going to pop up over and over again as you progress along in your engineering classes, in your other math classes, and your other engineering classes. You want to know how to do it, because it'll be very helpful. Okay, we'll do one more example on this. Let me know, anybody need more time to finish writing this down? If I don't hear from you, I'm going to think you guys are all set. Okay. So last example, example number 5. We have again y equals, if it's f of x, I just substitute it as y. I find it easier to take dy dx. F of x equals y equals x plus 1 squared times 2x squared minus 3 all over radical x squared plus 1. And we want to know what's the derivative. Okay, so the first thing I need to do is I need to take the natural log of both sides. So the natural log of y equals the natural log of my big block, x plus 1 squared 2x squared minus 3 all over radical x squared plus 1, like that. And now I'm going to use properties of logs. Break this up into smaller pieces. Okay, so this is going to become natural log of y equals, remember, I've got numerator and a denominator, so I've got things numerator minus denominator, so it's going to be natural log of x plus 1 quantity squared times 2x squared minus 3 minus the natural log of x squared plus 1, and I'll write this as an exponent. Okay, again, properties of logs, I have a product on the inside of my natural log, so I can break this up into natural log of x plus 1 quantity squared plus natural log 2x squared minus 3 minus the natural log squared plus 1 to the 1/2. We don't have an example here right now, but be careful if I've got a product in the denominator, there'll be minus the whole thing, and then that minus gets distributed to all of those terms in the denominator. So be very careful about if you have multiple terms in the denominator, that you don't lose track of your subtraction. You have to distribute that negative to all of those terms. Okay. All right, so let's deal with our exponents. So now this is 2 times the natural log of x plus 1 plus the natural log of 2x squared minus 3. I can't do anything about what's inside here because it's inside of a block. It's an equation on its own. Minus, I've got an exponent right here. 1/2 ln x squared plus 1. This is equal to the ln of y. Okay, so all we've done so far is just exploit our properties of logs. Our product property, our division property, our exponent property. Okay, now we're going to take the derivative of both sides. Okay, so I'm going to take the derivative of both sides, which means I'm going to take derivative here is going to look like 1 over y times dy dx. That's really important because I need to solve for that dy dx, right? This is my chain rule, but this is also what I'm aiming for when I go to solve. All right, now I'm going to go to take the derivative of all of this. So 2, this is my coefficient, times 1 over x plus 1 times my chain rule. My chain rule derivative of what's on side is equal to 1. Plus, right, I'm going to take the reciprocal of this. Oops, that's a 3. Now I have to do the chain rule. This is 4x minus 0, 4x minus the 1/2 hangs out. I've got 1 over x squared plus 1 times my chain rule times 2x. Okay. Let's clean it up just a little bit before we deal with our y. 1 over y dx equals, so this is 2 all over x plus 1 plus 4x 2x squared minus 3. This is 1/2 times 2, x all over x squared plus 1. And I know I can in theory find, one whole equation and bring them all together. I'm not going to worry about that. I'm just going to leave it as this, all these 3 terms here. Okay, now I get to solve for dy dx. Okay, I solve for dy dx by multiplying both sides by y. Okay, so let's write it out first. So dy dx equals y times 2 all over x plus 1 plus 4x 2x squared minus 3 minus x all over x squared plus 1. And now I have to substitute back in for y. Y equals our original equation here. Okay. So let's go ahead and do that. So my dy dx equals, my y equals x plus 1 quantity squared 2x squared minus 3 all over radical x squared plus 1 times, okay, I'm going to do this out, 2 x plus 1 plus 4x 2x squared minus 3 minus squared plus 1 there. And I'm going to put a nice big box around it. If I had done the quotient rule on this, I'd get the same answer. It might be in a slightly different form. Okay, so the quotient rule, like I would probably have had a common denominator, would have had terms combined across the top. Okay, and then my denominator is ultimately going to look like radical x squared plus 1 quantity squared. Okay, so it's going to look slightly different, but once I combine all the like terms, the form, the essence of it, the actual answer will be identical. Okay, but it may look slightly different because we're not combining like terms, we're just leaving it. Okay, you don't have to combine it and do all the algebra stuff. This is your derivative, you're done. Okay, and that's it for chapter 2.5. So technically we're done. Okay, I will scan this in and post it to our Canvas page later today. Chapter 2.5 and 2.4 homework are due next week. Okay, so you can have that to think about, and then we'll see. Probably 2.6 will be, I think 2.6 is due the week after. So don't sweat that one just yet. But anyway, so that's it for 2.5. I'm open to answering questions on the homework. If you guys don't have any questions on the homework, then you're free to go. And if nobody has questions on the homework, then we'll just end class early.
Sorry, Prof. I have one. Homework 2.1 question 49, but it's only for the part D and part E.
Okay, 2.1, let me get it out. 2.1, question 49.
Yeah.
Okay, okay. Let me just ask, is everybody done with this one? Because I'm gonna take this away. Anybody need more time writing this? Okay, so I'll scan this in later. Okay, you said 2.1,
Yeah.
question 49, right?
Yeah, 49.
Okay, great. All right, so let's take a look. Question 49. So let me just write down the questions. So we've got a particle position.
Yeah, it's very long question, so yeah.
It's not too bad, but we can talk about it. So this is 3t to the fourth minus 20t cubed, 24t squared plus 240t plus 1. Okay, and then t is in seconds, x is in meters, and then minus 3. Okay, so we're given a domain for t that we have to restrict ourselves to. Straight. Okay, and then what parts did you, let me just write down the answers to the different parts. So our velocity for part A was our derivative of our position, which gave me 12t cubed minus 60t squared minus 48t plus 240, and this was in meters per second. Part B, our critical points. Critical points I got in here were x equals minus 2, positive 2, and 5. That's where our velocity equals 0. I got that. I put this into a graphing calculator and I find out where that's passing through the axis. Okay, so you can use a graphing calculator. Okay, at this point we're not checking your algebra. We only worry about your algebra if you do it wrong and then you get the wrong answer, which is painful if you do all the calculus right. Okay, so our critical points, don't worry about factoring that. Part C. Part C was, we wanted to know where it was decreasing, right? X of t was decreasing. So I needed to take a look at, I'm looking at, I did, so I said increasing and decreasing. Okay, and then I did, so velocity at minus 3 I got was a negative number. Velocity at 0 was a positive number. The velocity at positive 3 was a negative number, and then the velocity at 6 was a positive number. So that gives me clues about like where the intervals over which it's increasing or decreasing. So from there, I could say it's increasing on the interval minus 2 to 2, and then from 5 to 10, and it's decreasing from minus 3 to minus 2. I don't have to go infinities, right, because I was bounded here. So this is 2 to 5. Okay.
Can we use negative infinity or positive infinity, or we just use negative 3 and positive like
Positive
like
10. Yeah,
yeah.
we're not using infinities because t, we were told at the beginning that t has a bound.
Oh,
So we have a restriction on our domain. We're only looking at t from minus 3 to positive 10, which is why we're looking here, why this is
okay.
bounded here at 10 and why this is bounded here at minus 3. So otherwise, you're right, we would have talked about minus infinity to positive infinity, but because we were told at the beginning to restrict our domain, right, then these are my restrictions. This is how I'm applying my boundary conditions.
Okay.
Question 32 on chapter 2.1. So let's take a look. So 32.
Professor Wilson, when you're done with that one, can you go over question number 40 on 2.4, please?
Yes, absolutely. Can you do me a favor and put that in the chat so I'll remember, because I won't remember when I finish this one here.
Okay.
So this was chapter 2.1. So question 32 on chapter 2.1. We're given f of x equals 6 sine of x plus 4x to the 6 minus 9 cosine of x, and my derivative is equal to, I'm just taking this in pieces, so 6 times, this is going to be cosine of x. This is my product rule, so this would be 24x to the 5th. And this is going to be minus 9 times a minus sine of x. So this becomes plus 9. So our derivative is 6 cosine of x plus 24x to the 5th plus 9 sine of x. That was it. Did you say you wanted to do 2.4? I'm sorry, wait, what was somebody just asked me a question about doing a question.
Yeah, it was
What
2.4.
question was it?
Question number 40.
On which chapter?
2.4.
2.4?
Yeah.
Okay. Question 40. Okay, great. All right, let me get up my notes. So 2.4 is due next week, by the way. I'm happy to answer it right now, but just to let you know, you don't have to pass it in right now. I think this 40 is a long one, right? Let me just check. Oh, is this the probability one?
Yes.
Yeah, okay, yeah. So I'll post the solution for this one, but I'll tell you, well, I'll just talk about the theory on it just really quick, and then the solution, there's actually a lot of algebra, but let me write it down, I'll post the solution. Chapter 2.4, question 40. And this is actually an excellent question because I think as engineering students, you guys are required to take Math 3081, which is probability and statistics, which I also teach in the summertime. Typically, it's a lot of fun. It's a really neat class. But this question leads right into that class because what we're looking at is the function that we're given is the normal distribution. This is when they talk about like a bell curve. Right, we're looking at a function that goes like this. This is our normal distribution. And the function is 1 over sigma radical 2 pi e to the minus, let's see, it's x minus mu squared all over 2 sigma squared. Now what happens is mu is your mean, it's your sample mean or your population mean typically. Sigma is your standard deviation. You've probably heard these terms a lot. Standard deviation, sigma squared is your variance. Same thing, right? But so I take the square root of my variance to get the standard deviation. Now what happens is you have to go through all of this is a constant, and this is, if I take this with respect to x, right, take the derivative with respect to x, what I'm going to get is 1 over sigma radical 2 pi, and it looks like it's a mess. So it's e to the minus x minus mu squared 2 sigma squared times, right, I have to do the chain rule. There's a minus in there, minus x minus mu all over sigma squared, right? So the 2's cancel out because I do the chain rule on that one. So now what happens is I have to set that equal to 0 and solve for x, right, to find my critical points, right? And then basically what you find is there's a lot of math. I'll put this, like I said, I'll put this whole solution up online so you guys can see it, but you find that your critical point is equal to x equals mu right here, which makes sense that this is where your tangent line prime of x equals 0, right? That's where our tangent line is horizontal. So this spot right here is our maximum on this function, which is, it's neat to see because we're often told we've got this bell curve, the middle of the bell curve, this, maximum point is our mean value. Mu stands for mean, right? Now, when I take the second derivative, there's a lot of algebra in here. I'm not going to write it down, but when I take the second derivative, set it equal to 0, and then solve for x, what I get, x is equal to mu plus or minus sigma, and these are our inflection points. And you often hear, like, I'll write it out here. So this is mu minus sigma, and this is mu plus sigma. And they correspond like to here and to here. So these are our inflection points. Now, we often hear, right, this is essentially, plus or minus, this is like 65% of our curve. The area under this curve if I go 2 standard deviations, mu, you know, minus 2 sigma mu plus 2 sigma, I've got 95% of my curve. That's my, you know, 95% of things happen within 2 standard deviations of the mean. You've heard that. Well, that comes from my inflection point is right here, right? Mu minus sigma. So we use this sigma now as like a, you know, kind of like a metric for let's count out how many sigmas we're going away from our mean, right? So it's a really neat thing. Like I said, there's a lot of algebra in it. It's a long question to answer just right now, but I will post it because it's a really neat thing. It's a really neat problem, and it is something that you will see in Math 3081, probability and statistics, which I think you're required to take. So great question. I'll post the solution because it's too long to do in class right now, but it's good stuff. All right, question 43 on 2.2. Chapter 2.2, question 43. Let me get mine out. Did I didn't post that one, did I? Okay, I read it. So this one, actually also this one is a long one too. If you guys are okay, I'm gonna post this one too, question 43, because it's quite a long, there's a lot of algebra and a lot of stuff. It took me about a whole page to do it out. So let me just, chapter 2.2, question 43. So I'll post that later today, just so you guys can see that. 43. And 37 and 39 on 2.3. Okay, so 37. So 37, so chapter 2.3, question 37 goes like, we want to find the critical points of f of x and g of x, and h of x equals f of g of x. So that's our function that we're looking at, right? And then we're given, let's see, f of x equals x squared over 2 minus 3x plus 1. And I'll write it down this way. G of x equals minus x squared plus 6 times. So my derivative here is going to be 2 times 1/2, right, minus 3. I set that equal to 0. X equals 3 is a critical point. Here I'm going to do the same thing. So g prime, I take the derivative, I'm going to get minus 2 times x plus 6, right? And I set that equal to 0. And I solve x equals 3 is a critical point. Okay. Now, f of g of x, I'm going to have to plug that in. So that's f of this function here, f of minus x squared plus 6x. Okay, which means everywhere I see an x on my f function, I plug in this big thing here. So it's going to be, I'm going to go 1/2 times minus x squared plus 6x squared minus 3 times minus x squared plus 6x plus 1. Okay, now I have to FOIL things out here and distribute things here to get one big term. So then I'm going to get, let's see, let me do it out. So it's going to look like minus x squared plus 6x times 2x minus 2x plus 6. There's a lot of algebra. Plus 6x minus 18. There's a lot of stuff going on. And then I set that equal to 0. So, whoops, I took the derivative. F of x derivative here. So I'm taking the derivative. All right. Right, there's a lot of, I distributed and then I just took the derivative. So now I set that equal to 0 and I solve x. So 0 equals, there's a lot of math, 2x cubed minus 18x squared plus 42x minus 18. I get x equals 0.55. X equals 5.45 and x equals 3. These are my critical points. So I needed to have a critical point from my combination. Sorry, you can see that. I need to have a critical point from my combination and a critical point from my g of x. My g of x had x equals 3. Okay. My bigger function f of x had x equals 3 as a critical point. So if that wasn't included here, I needed to include it in my critical point stuff. I have a critical point from their composition and I have a critical point from their individual function. Okay, I'm gonna, let's see if that was question 37 and 39. So I'll put up chapter 2.3 question 39 because we're running out of time here. So I'll put these up online, 2.2 43 and 2.3 question 39. I'll post those later today because we've run out of time. Okay, guys. All right, don't forget, homework's due tonight at midnight, 2.1, 2.2, 2.3. Plus we have a quiz that opens up today at noon. Okay, on those chapter sections. Okay, guys, don't forget no class on Monday. Okay, I don't think we even have a Zoom link for it. So I will see you basically in a week. Have a great long weekend. Bye.
Thank you.
Take it easy.
Thank you.